managed very well. So I haven't marked them, but let me start a note here. It's 120. Okay, so like I said, I haven't marked them yet, but once the tests are marked, oops, sorry, my fingers are completely raw from writing all day. Once the tests are marked, you will get an email from Gradescope. You will get an email from Gradescope to your My Okanagan email. So make sure that you check that, and that's how you'll be able to review your test and just see the comments that I've made and all that fun stuff. So so that's how the tests will be marked, and that's how you'll see how you did and stuff. Well, besides me posting the marks on Moodle. One thing that I wanted to say was there is a raise hand option in here, but what I find is when I am working in the other screen, so when I'm working over here, I can't actually see if you raised your hand. So it's just better if you use the chat option. So you should be able to find a chat option, and so that's where I let you know that that I was just wrapping up that meeting. And so if you send me a chat, if you have a question at any point, then just I should catch it pretty quickly. Who knows? Might, hopefully, if I miss it, you'll have to remind me. Okay. But otherwise, I'll just kind of keep going here. So once the tests are marked, then you will get an email from Gradescope, and it'll go to your My Okanagan email, just because that's how it'll be set up. So and we'll also do a bonus assignment. So we're going to do because as you noticed, kind of scanning and uploading and sending stuff to me, that takes practice, right? So what I want to do, because we want to use Gradescope for the rest of the things that you have to submit, just so you can show me your work and stuff. So you will have a bonus assignment where you will be asked to submit a Gradescope test document, just to get used to how it works. Okay. What's nice about it is that you tell me where you answered question 1, for example, where you answered question 2, and then you can make sure that I see everything that you did. Okay. So, what else in terms of housekeeping were we gonna do? All right, so my plan, because we did shift the tests up to last week, so that was kind of weird. And so what we'll do, so today we'll just kind of review chapters 5 and 6. So just kind of go back over, just so it doesn't feel so rushed, right? You already studied it for the test, but I just want to go back over it, fill in any cracks. And then on Friday, what we'll do is we'll start chapter 7. And let me just go check here on Moodle. I did try to change or update the setup here. So on Friday, we're going to do section 7.1 and 7.2. And you'll see I posted those lecture notes for the rest of chapter 7. And then on Tuesday, the following Tuesday, we will do 7.3 and 7.4. And then the next Friday, we'll do 7.5. And then after that, we've just got the Tuesday, I think, right? Tuesday, we'll do a review. We still haven't quite decided what the final exam will look like, whether it's a full-on final exam or if it's going to be just kind of a quiz, but we'll see. At least we've tested a lot of the material, so we kind of have some freedoms there. All right. Any questions? Go back to here. All right. Oops. I didn't want to stop sharing. It was a slip of the finger here. Okay. I wanted to see who was all here and check the chat. Nope. All right. Okay. So what we'll do is we'll just kind of go back through and I guess we can just kind of scroll through the 5.1, 5.2, or 5.1, 6.1 notes. So I can't remember. Oh, someone have a question here? I don't know who Vivo1818 is, but do you have a question?
Sorry, I don't have any question.
You don't have a question?
No.
No? Do you want to put yourself on mute?
Yeah, sorry.
That's okay. Awesome. Okay. So I feel like we got pretty well through 5.1 and 6.1 where we talked about the unit circle, right? So a circle with a radius of 1. And check this out, they gave me a fancy pointer. Hopefully it's not too laggy. Anyways, so we've got the unit circle, and what we said is if we start on this axis here, then we say we're in standard position, and then we end up at some terminal point. And if we move in the negative direction, then we're moving clockwise, then we're moving down the circle this way. If we scroll down to the radians, so a radian is an angle, right? But the definition of the radian is that if you've got a radius of 1, okay, then the radians here is going to be the length of the arc, right? That's subtend, and so we say subtends the angle. Okay? And so some common cutoff points, right, is that 1 radian kind of looks like this, and then we've got pi radians, which is half a circle, and then pi over 2 radians, and then of course 2 pi radians for a full circle, and then 2 radians is kind of more than 90 degrees. Okay. One thing to keep in mind, especially for this course, but also later in calculus, unless it says the angle is in degrees, right, the angle will be in radians, right? And so I'll make that a note on our end here. Let's do a little review from last day. Unless an angle is given in degrees, right, with the little degree symbol. And that's an open circle, I guess. Whee! All angles are assumed to be in radians. What that means for us, right, is on your calculator, we need radian mode on your calculator. Now, most calculators, most scientific calculators have a little R up at the top or a little D at the top. Right, so you want to make sure that you're in radian mode. Oops. And I think it's even RDC maybe. Let's see here. DRG is what mine says, so maybe I'll copy mine to make it look the same. So you've got D, you've got R, and you've got G. So kind of faint on your calculator screen, you want this radian mode. This is degree mode. Degree mode, radian mode. So you'll want to be able to check, and depending on your calculator, you can just, you know, Google your way to how to change from radians to degrees or vice versa. So. One thing that we didn't get to do a whole lot of last day, now where are these notes here, was just doing the conversions from radians to degrees. So let's have a look at that. Because we didn't really have to do it on the test, and so I'll just kind of go through it now. And let me steal some of these examples too. Around 6.1. So what we know, right, is that, well, we said 180 degrees. We know a circle that looks like this, right? If we go across here, this angle is 180 degrees. Oops, not percent. 180 degrees or pi radians. Right? So those are equivalent. And so that's what we use here when we're doing our conversions, right? So 180 degrees is the same as pi radians. And so 1 radian, so what we're saying here is that 180 degrees is pi, and we can just write rad. And so then 180 degrees divided by pi is going to be 1 radian. Right? And then same thing if we want to get, if we start at 180 degrees, oops, 180 degrees is pi radians, and just kind of shaking out the units, I guess. 1 degree is pi over 180 radians. So that's how we get these conversions here. So it says to convert degrees to radians, you multiply by pi over 180, and then to convert radians to degrees, then you multiply by 180 over pi. Okay. So all of these, we want to find the degree measure, right? So here, these are all in radians, all of these are in radians, and I know you guys want to do the harder ones. Let's do 26, for example. 5 pi over 18. If I want to find the degrees of this, I have the radians. of 5 pi over 18. And so to convert radians to degrees, I multiply by 180 over pi. So multiply by 180 over pi. So I get 5 pi over 18 is times 180 over pi. What's nice is these pi's are going to cancel because I'm multiplying. And even the 180 and 18 will cancel, but we don't have to do that. We can just use our calculator, right? And so 5 times 180, that's 900 over 18, puts me at 50. So that's going to be 50 degrees. Okay. What if I do 27? That's negative 2 pi over 15. Right? Again, I want to get these into degrees. The negative just means that I'm going clockwise. So I can ignore the negative and simply multiply by 180 over pi. So I get 2 times, and again, this pi and this pi will cancel. Definitely if you have pi's in there, then you are working in radians. It's extremely rare that we would have a pi in some sort of degree measure. So 2 times 180 puts me at 360 over 15. Oops, and I forgot the negative, but negative, so negative 24 degrees. Right. It's easier to think about these in degrees, right, than it is 5 pi over 18. So if you've got a circle here and you kind of switch it up, well, I know at this point, right, here's my 90-degree angle, split it up, well, kind of here, maybe this is 50 degrees, something like that. Right, just over half. Same thing here. If I split this up, let's see here. I know I'm going in the negative 24 degrees. If I think about, okay, well, a quarter of this is 90 degrees, and then half of that would be 45 degrees. What I want is probably half of that, right, ish. Half of that would be 22 and a half, so maybe I have to go a little bit more. Negative 24 degrees. Okay. So it would look something like that. Okay. Let me just check to make sure. All right. So, let's go back to those notes that you've got. Where are they? There. So, what we said is we've already talked about two angles being coterminal, but if two angles are in standard position, so they start here on this this positive x-axis, and then they go counterclockwise, as long as they end up at the same place. So if they're coterminal, it means that the sides that they end up with, right, well, they have the same terminal side, right? So what that means is that two angles are coterminal if their difference is a multiple of 2 pi radians or 360 degrees, depending on if you're working in radians or degrees. And so a lot of people have troubles with deciding if you should be in radians or degrees. But as a rule, if you see degrees, then you should be working in degrees. And if you don't see degrees, right, so if you don't see the little unit indicator, then you're working in radians. And usually radians would have some sort of pi, but not necessarily. Right? And so here, what we'll do, so I'm just going to steal this whole chunk, because we didn't really get a chance to spend a lot of time on this. Okay. Let's do, so the measure of two angles in standard position are given. Determine whether the angles are coterminal. Okay. And so as long as we remember that they're coterminal if their difference is a multiple of 2 pi or 3 radians or 360 degrees, right? Meaning that we've gone around the circle one time. Right, so from here, right, if we've gone a distance of 2 pi or 360 degrees, then they're coterminal. Okay. So if we have a look at, let's do maybe 38. 38 is 32 pi over 3 and 11 pi over 3. Now what I want to do, right, is I want to look at the difference, and so I'm just going to subtract 11 pi over 3 to see what the difference is. If it's a multiple of 2 pi in this case, right, then they're coterminal. So 32 pi over 3 minus 11 pi over 3, luckily I have the same denominator here, so I get 32 minus 11 is 21 pi over 3. And 21 pi over 3 so 21 divided by 3 puts me at 7 pi. So it's a difference of 7 pi. Well, that's not a multiple of 2 pi, is it? It's a multiple of pi, but not 2 pi. Not a multiple of 2 pi, therefore not coterminal. What if we do 40? Or actually, let's just have a look at one. Let's see here. Yeah, 40 is fine. 50 degrees, oops, 50 degrees. Let's look at the difference between 50 degrees and 340 degrees. So notice that now we're in degrees, so we need a difference of 360 degrees. So, or a multiple of 360 degrees. So we get 50 minus 340. Negative 290 degrees. Which is not a multiple of 360. Not a multiple of 360 degrees. So therefore they're not coterminal. This one's easier to visualize too, right? Because you've got, if you break it up into quarters, Well, 50 degrees would be somewhere around here. 50 degrees, and if I went to 340 degrees, probably end up somewhere around here. So they're not coterminal. Okay. For 41 to 46, I guess we can do it. We don't really work in degrees that often, so, but let's just do it for practice. So let's do, I don't know, let's do 44, for example, or maybe even, well, let's do 46. Sure. So 1,270 degrees. If we want to find an angle between 0 and 360 degrees that's coterminal with a given angle, well, so 1,270 degrees, what we can do is we can just subtract out a multiple of 360 degrees, right? And so, and we did that last day, right, where we said, okay, well, 1270, if I divide out as many 360s as I can, it looks like I'm gonna go around 1, 2, 3 times. What was that? Yeah, 1, 2, 3 times. Okay, that's 360 times 3 times. So that's 180 degrees. Oh, sorry, 1,080 degrees. So now the remainder that I need, right, is going to be 1270 degrees minus 1080 degrees. 1270 minus 1080 is 190 degrees. Oops. So from here, I need to go 190 degrees. I know halfway is 180, and then I need to go a little bit more. So here, right, 180 degrees, or sorry, 190 degrees. So this is my terminal end point. Terminal point, because that's where it's ending. Okay. Make sure no questions. Okay. All right. So that's how you're going to do those. And let's see, 47 to 52, do we need to find an angle between 0 and 2 pi that is coterminal with a given angle? All right, let's do one of those too. So same idea, right, except oh, I guess we didn't really answer, but the answer that we wanted for 46 is 190 degrees. And just cuts off all the other loops going around and around and around the circle. Let's do the same thing for one of these 47 to 52. Let's see here. Let's just do, number 52. 52 says that we have 51 pi over 2. So if we've got 51 pi over 2, then that's really 51 over 2, which we can say is 25.5 pi. This is just to be able to figure out how many times I've gone around the circle. right? And so, and this is where I flubbed it last time, right? We need 2 pi to go around the circle once, right? And so what I do in my mind is I just take 25.5, oops, 25.5 pi divided by 2, because how many times divided by 2 pi, I guess? I get 12.75, let's say, trips around the circle. Right? So 12 whole trips and then 0.75 it looks like. And so I get 5. So let's see here. I won't be able to draw 12 trips around, right? But we would have something like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, oops, 12, oops, ha. Time to only partially erase. Not that it matters terribly, but so here, that was 12 trips around. Okay. So that's the 12 trips around, and then I need another 0.75. So if I take away 12 trips, 12 times 2 pi. So here, this is 12 times 2 pi. That's the distance that I've traveled here, which is going to be 24 pi. Right? And so this distance that I need from here to the terminal point has to be 25.5 pi minus 24 pi. Right? So 25.5 minus 24 puts me at 1.5 pi. Right? Which is really just 3 over 2 pi, or 3 pi over 2 if you prefer, which we know from our cutoff points is just going to be, so here's half a pi, here's pi, here's 3 pi over 2. So the terminal point is here, and 51 pi over 2 has the same terminal side as 3 pi over 2. Nice. Okay. Just check for questions. Okay. So I think we'll leave 5.1 and 7 or and 6.1 there, and then we'll move on to section 5.2 and 6.2 if there are no questions. Okay. So 5.2 and 6.2, just go through and show you 2 different ways of evaluating trig functions. And so we can find trig functions using right triangles, right? Or we can use the unit circle. I suspect that for the test, you guys mostly ended up using a table like this, and that's probably, I mean, as long as you know how to use one of these methods, I'm happy with that. In calculus, you would have to know these values, right? So you would be expected to have these memorized, which might be tricky. right? And so I'll show you guys the special triangles. We'll go from there. Okay. So, let's see here. What did we talk about here? I'm assuming you guys know SOHCAHTOA. There's also kind of the less common cosecant, secant, and cotangent, okay, which are just the inverses of sine, cosine, and tangent. So you can know those as well, but yeah. What I want to do, well, I want to move this up to the top, but also let's use, actually, I'll grab this whole section. I guess put it there, and I'll do something like sections 5.2 and 6.2. This is more 5.2, but here we're going to talk about special triangles. To find key trigonometric values. Trigonometric values. Okay. Notice that these are in degrees. So what I want to do is I just want to convert these into radians. And so there's two triangles, and there's really no way about it. You have to just memorize these two triangles. But once you've got them memorized, then you don't need the table, for example. I'm going to try to make it as right angle as I can. Right? So I'm assuming that you guys are comfortable with the little square in the bottom. It just means that it's a 90-degree angle. And the angles inside a triangle have to add to 180 degrees, or just pi, right? If we're talking in radians. So in radians, this angle and this angle will be the same, right? Looking at this first triangle here, well, what it's saying is I've got a square, essentially, if you imagine this kind of square, both with sides 1, right? Then my angles in here are going to be the same. And so what I've got here is, well, it says 45 degrees, right? 45 degrees is, if we think about our unit circle, where it's kind of the easiest to visualize, well, here's 90 degrees. Half of that is 45. So here's pi over 2. So this must be at pi over 4. Right? So these angles in terms of radians are pi over 4 and pi over 4. Okay. By the Pythagorean theorem, right, this length must be √2. Okay. So this, this here, I would say, is the first special triangle to memorize. Okay. Why do I say to memorize it? Well, because if we have a look at the table up above, right, if my angle is pi over 4, then I have to be in this triangle, and it doesn't actually matter which side I'm on. We're going to end up with, it has the same opposite, the same adjacent, and the same hypotenuse regardless of which angle we're in, right? So it doesn't actually matter. But what we get is, if we've got pi over 4, then the sine of theta is the opposite. Wait, what the? What is it, root 2 over 2? See what I'm reacting to here? I don't have a 2 in my, 1 over 2, root 3 over. And yet, if I go to, let me just check. Sorry guys, just hang tight. It is root 2 over 2. Pi over 4. Here, I'll show you guys what I'm hung up on here. Because if we go and look at the next triangle, sine should be opposite over hypotenuse. Oh, heh, never mind, I'm on it. Okay, so if we're looking at, where am I here? If I want the sine of pi over 4, right? The sine of pi over 4 from the table we know is root 2 over 2. That took me way too long, sorry guys. So the sine of pi over 4, in terms of the triangle, right? I just need to go, so the sine is opposite over hypotenuse. So that's going to be 1 over root 2. But what we've done is we don't want the root 2 in the denominator, so then we multiply by root 2 over root 2. Yeah, oldest trick in the book. Can't believe it got me. Root 2 over 2. Right. There. How about the cosine of pi over 4? Well, the cosine of pi over 4, regardless of which pi over 4 I use, the cosine is the adjacent over the hypotenuse, so 1 over root 2 again. And so I get 1 over root 2, but same idea, multiplying by root 2 over root 2. Oops. Root 2 over 2. What if I want the tangent? The tan of pi over 4 is going to be, opposite over adjacent. So opposite over adjacent, so 1 over 1 is 1 over 1, which we can just write as 1, of course. Which now matches the table that we used before. And you can do the same thing, right? Knowing that the cosecant is the inverse of sine, and then the secant is the inverse of cosine, and cotangent is the inverse of tan. You can do the rest of those. But I'm going to focus my efforts on sine, cosine, and tangent because they're the most common and they're the ones that we'll need for sure. Okay. So this is the first special triangle, and this is how you'll be able to just kind of easily figure out what these angles are all about. So the other triangle that we have is going to let us cover 30 degrees and 60 degrees, but first let's convert that to radians. So in radians, we have, and it makes up half of oops, of this kind of a triangle. Works both ways, but we only need 1/2. Yeah. So as you'll see, right, we've got 60 degrees in the bottom and 30 degrees at the top. So 60 degrees is going to be what? 60 degrees and 30 degrees. 60 degrees in radians is, so 60 degrees, if we want to convert it to radians, remember, to convert degrees to radians, multiply by pi over 180. So 60 degrees times pi over 180 degrees is 60 divided by 180, which is pi over 3 radians. Right? Same idea here, 30 degrees in radians is 30 degrees times pi over 180 degrees. 30 divided by 180, I get pi over 6 radians. Right? So we can rewrite this triangle as something like, should have made it bigger, I guess. Pi over 3 and pi over 6. And then the lengths of these sides are 1 and 2, and then root 3 by the Pythagorean theorem. 1, 2, root 3. This right here, this is the second special triangle to memorize. Now, I know you're going to be doing the rest of your tests from home, but I mean, once you get to calculus, you will be expected to have these special triangles memorized. So if you ever need them, you could always rememorize them then, but just so you know that that's expected. So now we can go ahead and just confirm some of these values, right? For pi over 6 and pi over 3. So let's find just the sine and cosine. Oops. Sine of pi over 3, for example. Well, if I'm down here at pi over 3, if I want the sine, that's opposite over hypotenuse. So then I've got root 3 over 2, which looks to me, so the sine of pi over 3 is root 3 over 2. That's what we got. Let's do cosine and then let's do tangent. Let's do the cos of pi over 3, just using the special triangle. So the cosine is adjacent over hypotenuse, which should be 1 over 2, which, if you remember from that table, right, that's what we just saw. And then the tangent of pi over 3, what we're expecting to get is root 3. And so the tangent of pi over 3 to opposite over adjacent root 3 over 1, which is just root 3. And so these all confirm the values in the table. So that's why you only need to know one of the ways, right? Let's do the same thing for the sine of pi over 6, and then the cos of pi over 6, and then the tan of pi over 6. And how about we do them first, and then we can confirm. So the sine of pi over 6, so now I'm over here, the sine opposite over hypotenuse puts me at 1 over 2. The cosine of pi over 6, so now I'm up here, so adjacent over hypotenuse, root 3 over 2. And the tangent of pi over 6, so opposite over adjacent, 1 over root 3. 1 over root 3. So now let's confirm on our table here. So we've got 1/2 root 3 over 2 and 1 over root 3. For pi over 6, I've got 1/2 root 3 over 2. Okay. Root 3 over 3. That's okay. We know how to handle that, right? Because we got 1 over root 3. Now I can just rewrite that as times root 3 over root 3. Then I get root 3 over 3. Right? And that's how it's matching. If you left it as 1 over root 3, that would be fine, right? It's just to get it to match the table. Okay, nice. Check for questions, none. Yeah. Let's see what else this set of notes had. Okay, so let's do some of these. Oh, it's blurry. Anyways, so we're going to evaluate these expressions without using a calculator. I'm really only interested in the ones that are in radians, and so just being able to read these and see which ones are in radians. There's only 2, right? And so those are the only ones that I'm actually interested in. And let's start with 29. We want to find the sine of pi over 6 plus the cosine of pi over 6. We just evaluated these, right? So the sine of pi over 6 is 1/2, and the cosine of pi over 6 is root 3 over 2. So I get, that's 1 over 2 plus root 3 over 2. Luckily, I have a common denominator, right? So I get 1 plus root 3 all over 2. And I would probably just leave it there. I don't see what else I can do. Doing the same for 34. 34 is a biggie, right? So I've got the sine of pi over 3 times the cosine of pi over 4 minus the sine of pi over 4 times the cosine of pi over 3 all squared. Yeah. Treating each of these as individual numbers, right? We can just swap those out with what they're worth, let's say. So the sine of pi over 3 is root 3 over 2. So let's start there. So we've got root 3 over 2 times the cosine of pi over 4. The cosine of pi over 4 is root 2 over 2. Minus the sine of pi over 4. The sine of pi over 4 is root 2 over 2 as well. Times the cos of pi over 3. Cos of pi over 3 is 1/2. Times 1/2 all squared. Okay. A couple of different things coming into play, right? Because we have to simplify this and simplify this before we can subtract them, but also we've got that common denominator, so that's lucky, but also even when we multiply through, we still keep that common denominator. So what we have is root 3 times root 2 over 4 minus root 2 times 1 is just root 2 over 4 squared. So now I've got this common denominator. Common denominator. So I can rewrite this as root 3 root 2 minus root 2 all over 4, and then square that. What I'm going to do is I'm going to pull out this common root 2 just to see if I can simplify it a little bit better. So I get a common root 2 times root 3 minus 1 over 4 squared. Okay. What I can do here is I can now pull this square inside, but I have to pull it on all the things that are being multiplied. So I get root 2 squared times root 3 minus 1 squared over 4 squared. So I get 2 times root 3 minus 1 squared over 16. 4 squared is 16, but also I can cancel out a 2 here. 2, replace this with 8. So I get root 3 minus 1 squared over 8, and I would say that's as simple as we can get it. You could expand this thing, but I wouldn't bother. Check for questions here. None? Okay. Let's see here. All right. I'm just reading through the notes here. Okay. Making sure I don't skip anything too bad. But no, I think we got through all of this pretty well. This stuff where the functions are positive or negative, we'll come back to that when we need it, right? That's when we're figuring out our reference angles. Sorry, just so dry. Okay. So we did do this, but I think it's worth mentioning again. And we did do all of those. And let me just flip through and see. Okay. I'm wondering if we should just go on. No, it's okay. Let's do a couple of these. So I think I copied that, and I'll put it in here. So here, what we want to do is we want to try to evaluate trig functions for any real number. So it doesn't just have to be, pi over 3, pi over 4, pi over 6. It can be just any real number. And so the steps that we've outlined here, first thing we have to do is find the reference number, which is kind of the same thing that we were doing right when we were finding how many times we'd gone around the circle and then what the point was that we ended up at. Then we're going to find the sine. So that's going to depend on what part of which quadrant, which of the 4 quadrants we're in. And so this is where I guess we use this here. Maybe I'll shrink this up a little bit. So finding the sine, right, is going to be here. And so remember, it depends on if the x or the y is positive or negative. So we want to find the sine of the trig function. And then we have to find the values. So if we find the value, then we might have to change the sign as we move around in these quadrants, but everything else stays the same, right? And we saw that in our unit circle too, right? So here, as we move to a pi/6 point, the x value was always √3/2. It just depended on if it was positive or negative, negative, and then back to positive. So let's do a couple here. And I think we did a lot of these last day. Well, let me can just do them again. Does anyone remember if we did, I feel like we did some of these for the practice test. 5.2, 6.2. So we did look at between 5 and 10. Also, we did do these last day. I feel like you got those under control. Let's just do a couple then. And just so that it's just. Let's just solidify 5, 6, and 7, just so we have the instructions for what we're doing too. So find the exact value of the trig function at the given real number. And so we've got sine 7pi/6. And so what we've done, right, is we've got, all right, let's see here. We've got the sine of 7pi/6. 7pi/6 is, if we look at this, right, we've got a pi/6, so we know kind of what's going on. But 7pi/6 puts us here at some fraction of pi/6. And so if I've gone 7/6 of a pi, right, then here is 1 pi. Oop. So this is 6pi/6. And then if I go another pi/6, then that puts me at a total of 7pi/6. Right. And if I want the sine of that, well, that's going to be, I've got an angle of essentially pi over 6. And sorry, I'm glad we're not meeting in person, actually. I'm coughing and so snotty. I'm running my nose everywhere. It's probably for the best. Let me do this in a different color so it's not as confusing. So this distance here is 7 pi over 6. And so from my special triangles, right, I know that if I've got pi over 6 here, then what was our triangle? What did our triangle look like? Is 1, root 3, and 2. 1, root 3, and 2. So if I want the sine of this thing, right, sine opposite over hypotenuse, so 1 over 2. So sine of pi over 6 is 1 over 2. Okay. But here, sine is going to be, and this is where we need to know where, and I'm over here, right? Where sine Hello? Okay, so we need to know where sine is positive. And so in quadrant 1, all of the functions are positive. In quadrant 2, sine and cosecant, so let's just talk about the sine, tan, and cotangent, or cosine. And so here all of them are positive. Here only sine is positive. Here only tangent is positive. And here only cosine is positive. So you can remember it as all students take calculus, right? As you kind of, and that's the, some elementary or some high school teachers use CAST. So kind of starting down here, but to me it makes more sense to start in the first quadrant. And so all students take calculus. And so this is how you'll be able to remember which ones are positive in which quadrants. So sine is only positive in the first and the second quadrants. So we can make a note of that. That sine is only, and I'll put sine is only positive in the first and second quadrants. Okay. And so here, I'm in the third quadrant. So therefore, sine of 7 pi over 6 must be negative 1/2, since it is in the third quadrant. I'll let you guys, if there's any questions. All right, let's see here. None? Okay. So just flipping through here and kind of keeping an eye on the time. Let's keep going to section 5.3 because we did spend some time doing these, I guess, last day. So, but definitely go through and review them and make sure that you've got them all under control. And then let's keep going to 5.3. So 5.3 is for graphing. And so section 5.3 is just the one page, I guess. And Oh. If we're graphing sine and cosine, then what we've got is, because we said, and you know what, I'm going to do a little, oh, thank you. I'm going to do a little scribble here so that I can say that it's been edited. Sorry. Okay. So sine and cosine, we talked about them, and you're probably familiar with sine and cosine anyways, but sine and cosine, right, they're periodic. And so if you've moved a distance of 2 pi, right, you end up at the same value that you would have started at if you just started on sine. So here what we're saying is sine and cosine have a period of 2 pi. Okay. So it's cyclical, and so we just kind of end up at the same spot over and over again at a kind of a rate of 2 pi. So sine and cosine, right, we already had a look at all of these tables, right? And so here we're moving through a circle essentially. So here, moving up and down, and the most important part of this section is just being able to graph and shift a sine and cosine curve and knowing what it looks like. And so here, I actually feel like we did, although we went fast last day, we did do a very thorough job of going through these. So I don't feel like you're too underprepared. The key, right, is in drawing or in graphing sine and cosine curves, sine and cosine curves, we need to get them in the form y equals a sine k x minus b, and y equals a cos k x minus b, as long as k is greater than 0. Right, we can't have a multiplier that's negative here. And so, right, the only difference between these two is sine and cosine, but really how they behave are the same, right? So these two, they have an amplitude. Amplitude is the absolute value of A, where the amplitude is just how far, if you've got your sine curve, for example, that's not a very beautiful sine curve, but that's okay. So sine of x, this distance here, this distance is the amplitude, which is the absolute value of A. The next thing that's in that definition is that the period is 2 pi over k. And I have a feeling that these are slightly different from what you have on your formula sheet, but just in terms of the notation, so not the ideas though. So if you've got k, right, then the period is going to be 2 pi over k. Usually k is 1, so then the period is just 2 pi, which is the default for these things. And so a period goes from here and just kind of goes a whole cycle until we're back to where we started. And so this distance is the period. Yeah. And the default is 2 pi. And there's a horizontal shift. Horizontal or phase shift is what we were calling it, just to match the formula sheet that you have. So the horizontal or the phase shift is just how much you've shifted to the right or to the left. And so here, right, if you've gone from here, the phase shift is 0, right? Whereas if the curve started here, and just kind of, and this would be the phase shift, right, to the left or to the right. So the phase shift is B, right? And it's positive if it's to the right and negative if it's to the left. One thing to keep in mind, right, is that you've got minus B in here, right? And so if you've got something like x plus 2, then B would actually have to be negative 2, right? And so I'll put it in a different color. If we have x minus or x plus 2, right, and we have to write it, then that's x minus negative 2. So B would have to be negative 2, right? So that's when we have a shift to the left. So it's a little bit sort of backwards, I guess, in a way, but that's just how it is. So that's the only sneaky part that we have to keep track of. Okay. Let's see here. What do we want to do? Guess let's, really don't think you'll have to graph that much, and so I just want to do a couple maybe from here on out. Let's do some of these. Let's steal all of them, pick from there. Okay. So if we've got something like, well, I think we did all the ones until 38, right? And then we said, well, it wasn't going to be 37, but let's have a look at something like 40, right? That wasn't on our practice test because it wasn't going to be on our test, but let's have a look at 40. So we've got y is 2 sine 1/2, oops, my eyes deceived me, 40, 2 sine 2 over 3x minus pi over 6. Okay. Let's find the amplitude first. Or I'm going to shift this down just a bit here. A is 2, right? Matching it to y equals a sine k times x minus b. So y equals a sine k times x minus b. So a must be 2. And what I can do is I've got k times x minus b. So here's the problem, is that k is on the outside, right, times x minus b, and I've got 2 over 3 times x minus pi over 6. So what I'm going to have to do is I'm going to have to pull out a common factor here, and that's my k. I need x on its own here, so I need k to be 2 over 3. So whatever I have to do to pull 2 over 3 out of pi over 6, that's what I have to do. So what I'm going to do, I guess I'll delete this. It's premature, I guess. I have to rewrite this as y is 2 sine 2 over 3x minus, and then what I have to do is I have to do pi over 6 divided by 2 over 3, right? Because I have to divide out that 2 over 3. Okay. Now we've got a fraction over a fraction here, which we know how to deal with. And so it's going to get messy for a little bit here. 2 sine 2 over 3 times x minus, and then I've got pi over 6. So fraction over a fraction, remember you just kind of use your fingers, you flip and multiply, and so that 2 over 3 becomes 3 over 2 that I can multiply. And so what I get is I get y is 2 sine 2 over 3 times x minus 3 pi over 12. 3 pi over 12, I'm going to simplify a little bit here. So 3 over 12, I can rewrite as 1 over 4. So I get y is 2 sine 2 over 3 x minus pi over 4. So what I get, now I can say, okay, well, a is 2, k is 2 over 3, and b is pi over 4, positive, right, because they're already being some x minus b, right, just to match y equals a sine k times x minus b. So now what I want to do is I want to kind of sketch this graph, and you didn't have to do this, you just had to pick the right one, and we'll only do this one, so it won't be too bad. So what do we have? We've got the amplitude is going to be 2, the period, so now we're ready to do it. So the amplitude is the absolute value of a, which is 2 in this case. So I know the height of this thing has to be 2 from the x-axis to the peak. The period is 2 pi over k. So in this case, that's going to be 2 pi over 2 over 3, which we can rewrite as 2 pi over 1, right, to rewrite it as a fraction. And then I guess technically, if you want, over 2 over 3, just to show that it's a fraction over a fraction, right? 2 pi over 1 over 2 over 3 becomes 2 pi technically over 1 times 3 over 2, puts me at 6 pi over 2, or just 3 pi. So my period is going to be 3 pi. So what it takes for me to go a whole cycle is going to be a little bit stretched out, right? And I know that this distance here must be 3 pi now instead of 2 pi. And then just to show the amplitude is 2 instead of 1, which it is by default. Finally, the phase shift is pi over 4. The phase shift is B, which is pi over 4, which means that from here, I've gone out to pi over 4, and that's where my sine curve is starting. Okay. So now I can combine these to sketch the graph. And so now I'm going to sketch the graph. So one thing that I know, well, I've got my X and Y axis here. I'll make this 2 and this -2. Sine and cosine, right, have to be between, and just to give myself a little guide here, I'm just gonna draw these kind of bands. And let's see here. If I've moved out pi over 4, then here I might be at 2 pi over 4. Here I'm at 3 pi over 4. Oh, maybe that's too short of a distance. Maybe I want to do distances of pi instead. Pi over 4, oh, whoops. Pi over 4, if I want to move out pi, then that puts me at 5 pi over 4. Somewhere here. If I move out another pi, that should put me at 9 pi over 4. If I move out another pi, that puts me at 13 pi over 4, and so on and so forth. And so here, each of these distances are pi. Oops. Which I also happen to know is my period, right? If I've moved 3 pi, that's the period. Yeah. So all I know about this curve is, well, let's use a different color here, is it starts here because it's a sine curve, right? I've shifted it over. I'm going to stretch it out. So the next time I end up here, well, not really, I have to cross the axis once, but the next time I start over is going to be at 13 pi over 4. And so here, and I'm going to go an amplitude of 2. So the halfway mark here is going to be at 1.5 pi. Right? So this is where I'm going to go cross over. So what it's going to look like is I'm going to go wee. Something like that. I'm pretty glad that you guys didn't have to do any sketching on your own on the test, and because it's pretty time consuming. I think that was good. Okay. You guys will stop me if you have questions, right? Maybe, maybe not. For the last little bit, let's just touch down in 6.4 just to kind of see it again and just review it a little bit. And then, like I said, next day we'll start chapter 7 and just kind of keep going in chapter 7. And you've got those notes, so I mean, I can't get you printed notes anymore, so you're on your own for that, but maybe just having them online is okay. That's how I have them. All right. Let me just make a little mark here. So inverse functions. Some key things that we didn't really talk about last day are things like the domain of an inverse function. So from section 6.4, so the sine, cosine, and tangent functions, right? Sine and cosine keep going forever and ever and ever, right? And so they go like this, sine, b, wee, right? Cosine, so, oops. Sine of x, cosine of x starts down here, wee. So remember, I just do them kind of alphabetically. So cosine starts up here and sine starts down here, right? C comes before S, so it starts up here and then they just kind of fishtail around each other. Okay? To find the inverse of a function, right? We have to have a one-to-one function, which is not actually the case, right? And so what we have is we have to restrict the domains from negative pi over 2 to pi over 2 for sine, and then 0 to pi for cosine. And then we haven't really looked at the graph of tangent, but we restrict it to negative pi over 2 and pi over 2. And so we can restrict this. Let's see here. So this actually goes down like this. And then of course this keeps going. I don't know, muck that up. So the inverse of sine has a domain from -1 to 1 and a range from negative pi over 2 to pi over 2. So what we've done is we've taken from negative pi over 2 to pi over 2. Sine is invertible, right? Because then we're only looking at this little section. So for all these, there's only one output for each input. Right? So for example, sine is invertible on the interval negative pi over 2. Oops, should use proper notation. Pi over 2 to pi over 2. And so we limit the domain, and so therefore the inverse of sine has a domain has a range. Has a range of negative pi over 2 to pi over 2. Oops. This is all coming from before. Recall, a function is invertible if it is one-to-one. And if f of x has domain, so this is just in general, has a domain from A to B and a range from C to D, then the inverse of f as the domain of the original range and range, the original domain, right? So they kind of flip-flop back and forth. That's not something that I kind of expect you to remember or anything like that, but it is good to keep in mind, right? So here, the domain that we're interested in for sine is going to be from -pi/2 to pi/2, and so sine inverse has a range of -pi/2 to pi/2. Yeah. And we're not going to bother too much with tangent. Let's see here. So the sine inverse of x, if it's y, then what we know is that we can replace that and rewrite that as the sine of y equals x. In fact, I'm going to rewrite it this way. X is the sine of y, right? Just because what we've done, right, is we've taken the sine and brought it over here. And we used that fact when we were composing the trig functions. So we did way harder things than these little, and I feel like you were doing really well. Let's just do one. Let's just do question 4. And I think that should be good for today. Okay. So if we want the sine of cos inverse of 5/13, then what we're saying, oops, I'm going to move this down here. We let theta, which is just kind of a universal notation for an angle, be the cos inverse of 5/13, right? Because what we're doing is we're replacing this with theta for a little bit, right? Because what we just established is, and this all works for cosine as well, right? So what we know is that cos inverse of x is y also means that x is the cosine of y, right? So here I've got the cos inverse, which I can move to the cos of theta. And so now I've got the cos of theta is 5/13. So if I'm told that theta is here, and I know that the cosine of theta is 5/13, well, that means so cosine is adjacent over hypotenuse, so that means I've got 5 and 13 here, right? And then I can use a squared plus b squared equals c squared to solve for that last one. And so if I let a is 5, b is question mark, and c is 13, right? Then I've got a squared plus b squared equals c squared. 5 squared plus b squared equals 13 squared. So 13 squared is 169. 5 squared is 25 plus b squared. So b squared is 169 minus 25, 144, so b must be 12. It is. So then here, b equals 12. So now right? What we did was, okay, we say sine of theta. Well, I've got theta here. So sine is opposite over hypotenuse. So the sine of theta is the opposite over hypotenuse, which must be 12 over 13. And that's it. All right. Any questions from my probably, yeah, 2 participants? No? No questions? Oh. No questions? All right. That's good. Awesome. Then that's it. That's all I've got for today. So I will, well, you'll hear from me on Friday where we'll start chapter 7. But I think it's a good idea if you just review the chapter 7 notes that I posted beforehand, especially because I don't get to print them off for you guys. All right. Well, thank you. All right. See you guys next time. Bye. Thanks, Arvinder. Yeah.